Hi, everybody. My name is Matthew Powers. Very happy to have you all here. I'm with Youssef, and we're going to be chatting about the best features of Delta Lake and why you should love your open tables. Okay, here's what we're going to cover in the talk today. We're going to be chatting about the Lakehouse architecture, how we've kind of migrated from the Lakehouse architecture now to this data intelligence architecture. We're going to be chatting about how Delta tables provide you with reliable transactions, things like rollbacks. We'll talk about how Delta is compatible with tons of different engines, including Pandas, Polars, Data Fusion, PySpark, and tons of others, actually. And we'll also talk about why we get much faster queries thanks to file skipping. Then I'll pass it off to Youssef, and he'll talk about some other features.
Yeah, we'll be talking about deletion vectors, and how you can do a powerful merge operation, schema evolution, generated columns, constraints, and checks for data quality. Last but not least, liquid clustering with Delta 3.0.
Sweet. All right. Let's take a look at the evolution of kind of how organizations have been architecting their data systems. So in these first generation platforms, or organizations were kind of ETLing structured data into data warehouses for BI and reporting purposes. Now that worked great until organizations wanted to take advantage of advanced analytics like data science and machine learning. So then organizations started taking a data lake, ETLing part of it into a data warehouse for BI and reporting, and then just querying the data lake directly for data science and machine learning. Now, as you can see in this two-tier architecture, data was being duplicated in the data lake and the data warehouse. And anytime we kind of violate the single source of truth data management principle, we know there's going to be some pain and suffering. Another thing that wasn't great about this two-tier architecture is that querying data lakes directly, first off, is unreliable, and second off, isn't performant. So it wasn't great for data science and machine learning. So then about 5 years ago, organizations started migrating to this Lakehouse architecture, where data was stored in open tables, such as Delta tables. And those Delta tables were performant enough and reliable enough to be queried directly for BI and reporting purposes. And they were also flexible enough to be used in data science and machine learning analyses. Now, modern organizations want more, which is great. We want to give you more. So Delta tables are still the foundation for structured tabular data. And what organizations want in their data intelligence architecture, in addition to this, is governance and security, which can be handled with the Unity catalog. And organizations also want to use Gen AI to understand their specific data sets. So they want to create custom AI on their data. So that's kind of the defining factor of the data intelligence architecture. Now, what's cool about the data intelligence architecture is, since data is being stored in these open tables, it can be queried by a variety of engines, including Photon, Spark, PyTorch, Ray, and Pandas. So you get to kind of use the best engine for your analysis. Okay, let's dive in with a quick example here, see how to create a Delta table, and then see the power of the rollback feature. So on the top left there, you can see the create the Delta table section. What we're doing there is we are instantiating a Pandas data frame, and then we're going to write that out to a Delta table. I'm intentionally using the Pandas library just to show how interoperable it is with Delta Lake. Then in section 2 there, we're instantiating a second Pandas data frame. It has a single column ID, 2 rows of data, 4, 5. We're using that write Delta Lake method again to write to our Delta table. But in this case, we're setting the save option to overwrite, which is going to perform a logical delete of the data. So a logical delete is different from a physical delete. So a logical delete means we are marking the file, the initial data file, for removal in the transaction log. We're not physically removing the Parquet file from disk. Then we are going to instantiate a third data frame, third Pandas data frame that has a single column ID, 3 rows of data, 7, 8, 9. We're going to write that out to a Delta table. So now we have a Delta table, as you can see on the right, with 3 different versions. Version 0 has 3 rows of data, 0, 1, and 2. Version 1 has 2 rows of data, 4 and 5. And version 2 has 3 rows of data, 7, 8, and 9. So let's take a look at how we can roll back to version 1 of the data table. So if we read this delta table, by default, we're going to get the data contained in version 2. Now, what's really cool about delta is it stores version data sets, so we can temporarily time travel between the different versions, or we can kind of permanently roll it back to an earlier state. So in section 2 there, you can see we are using PySpark. We're going to instantiate a delta table object, and then we are going to invoke this restore to version function, our method. We're going to supply the argument 1, so that's going to restore back to version 1 of the delta table. So you can turn your attention to the bottom of the screen, confirm that the correct data is read. Now we can see when we read the delta table, it's going to read in the data as of version 1 because we've rolled back to version 1. So I love that. The reason why restore is so powerful is because if you make a mistake, you can undo the mistake. That's not an option when you're using a data lake. Let's look at the reliable transactions that are provided by an open table format like Delta Lake. So in section 1 there, we are instantiating a PySpark data frame, and then we are going to write that out to a Parquet data lake. Now, writes to Parquet data lakes, or any transactions to a Parquet data lake, are dangerous. So we're not guaranteed that that's going to complete fully or fail fully. So we can get in an uncomfortable situation, like let's say you're performing a big write to a Parquet data lake, and then in the middle of the write, your cluster dies, and then you kind of just have these zombie Parquet files that are just partially written and corrupt. With a Parquet write, it's just too bad. You're not in a happy place, and you'll need to do manual cleanup. Now, if you look at section 2, appending to a delta table safe, we can see that this equivalent write operation to a delta table is safe, and it has the properties of an ACID transaction. So this transactions are useful whenever you do things like operations like deleting rows, appends, upserts, overwrites, and compaction operations. And with a delta table, we're ensured that the transaction is going to either complete fully or fail fully, but nothing in between. We also have checks to make sure that the constraints of the table will be made, and there's schema enforcement as well. Cool. All right. Now let's look at a completely different feature, which is reading a delta table with the Data Fusion query engine. So suppose we have that delta table in section 1, and this delta table contains 9 columns of data. And then in section 2, we are going to instantiate that delta table object and also instantiate a Data Fusion session. Data Fusion, by the way, is a very powerful query engine for single node analyses. So then what we do is we register this data set with Data Fusion, and you can see what we are doing to make this delta table readable by Data Fusion is we are actually exposing it as a PyArrow data set. Now, this is really cool that we can it's really cool on two fronts. First off, it's cool how easy it is to expose a delta table as a PyArrow data set. And it's also cool that Data Fusion is capable of seamlessly just reading PyArrow data sets. So then we can see at the bottom, we can execute a SQL query no problem on our delta table. Now, what's really amazing about this is that Delta is interoperable with Data Fusion, even though we haven't constructed the official connector yet. Let's turn our attention to a different query engine, Polars. Here we have that same 9-column data set from before. It has 1 billion rows. And let's see what a Polars query looks like running on this data stored in a CSV file. So this is a pretty straightforward query. What we're doing is we're running a filtering operation and then running a group by sum aggregation. And when this data is stored in CSV file, it takes 30.4 seconds to execute. Now, if we simply convert this data to a delta table and run the same query using the built-in Polars scan delta function, we can see we're using the same filtering group by sum aggregation logic. We can see that this just takes under a second to run now, specifically 836 milliseconds. Now, you might wonder, why is this so much faster? Well, the vast majority of this performance gain is because, obviously, delta tables store their data in Parquet. Parquet is a more efficient file format to query compared to CSV. So that's going to be the vast majority of the performance gain. But the other component of the performance gain is that Delta tables store file-level metadata in the transaction log. So when when Polars is executing this query, it's looking at this filtering logic and saying, well, I'm just looking where ID is equal to ID 016. And it can look at the file-level metadata when it's running this query and just read a subset of the files that have data that's relevant for the query. That allows for file skipping, which is a huge performance benefit. So any engine that's reading a Delta table can take advantage of that file skipping, which is a huge performance benefit. This is just kind of a fun example showing the interoperable nature of Delta. So in section 1 there, we are creating a Delta table with PySpark. We're instantiating a PySpark data frame and writing it out to a Delta table. So that's our initial creation operation. That writes 2 rows of data. Then in section 2, we are instantiating a Pandas data frame and appending it to that same Delta table that we just created. And then in section 3, we're going to read in that Delta table using the Polars engine. So we do that with the built-in read Delta method, and we can see we have our 3 rows of data as expected. We're reading in the 2 rows of data that were from the initial PySpark write, and the final row of data from the Pandas append. So I just love these kind of examples. Delta is so interoperable. So we've talked about a few engines thus far, but of course, Delta's connector ecosystem is way huger than what I've explained or presented thus far. I wouldn't have time to talk about all these different engines. But basically, Delta is interoperable with all these engines, and the level of interoperability is going to get even better. So like Delta, like the Scala implementation obviously supports the most amount of table features. So table features are things like deletion vectors and liquid clustering and schema evolution. The Delta spec is continuously evolving. Now, one thing that's really hard when you're maintaining a huge network of connectors is keeping them all up to date with the latest features. So what we've done is we've built this Delta kernel project. There's 2 implementations. One implementation is in Java, another's in Rust. And these kernel implementations are going to contain the core bits of logic, which are going to make it so that the Delta connector ecosystem is maintainable and everybody can get a full-featured connector. The last thing we want is a connector, for example, like let's say Trino is unable to read Delta tables with deletion vectors enabled. We don't want that. We want all the connectors to be able to support all the features, and that's going to be possible with Delta kernel. Cool. My last little rant before I pass this off to Youssef is that Delta Lake is great for small data too. So I think most people know that Delta is a technology that can be scalable to some of kind of the largest data tables that actually exist on the planet. There's folks who are ingesting hundreds of terabytes or even petabytes a day into Delta tables. But a lot of the features that Delta provides are equally useful for small data sets. So for example, ACID transactions, time travel, the rollback feature we covered, the interoperability, schema evolution, schema enforcement, constraints, a bunch of these features that Youssef is about to talk about. Those are great for small data too. So make sure to consider Delta Lake even if you have a small data set. Cool. I'm going to pass it off to Youssef, and he will guide you through the rest of these features.
Hey. I need to raise my voice. Yeah, we're good. So full disclosure, the order of the features doesn't matter, although I managed to get the coolest features. That's important. I've been rehearsing this in my mind for like 15 minutes. Okay, now we're gonna talk first about deletion vectors and why they are super important. But before, let's set up the ground. So delta is Parquet plus some logs. And you may know that Apache Parquet is immutable, which means like whenever you're doing a merge, update, or delete, a new Parquet file is rewritten, which means if you're like doing multiple transformations, you ended up doing a lot of rewrites. And those new files will contain like either the new added files or the deleted files. Why? Because Delta protocol has only support for what you call copy and write, which means like the underlying files are rewritten every time there is a change in the code. While with deletion vectors, we're introducing a new paradigm called merge and read. and in which like the underlying files are not changed, and they are rewritten separately for readers to merge when they are being read. So to summarize, deletion vectors removed the need to rewrite the files whenever you have an operation like read and write. So basically what they're doing, they're tracking the rows that are going to be changed in a bitmap to make sure that we reduce the number of writes. And these deletion vectors was able to improve the performance up to 10 times. So trust me, you need to enable this feature. And what about schema enforcement? So you may know that while using your data lake, you may have, for example, a table, I don't know, called the customer, name, and last name. But for some reason, a developer is working on this specific data frame, and then he tried to update this table by adding a third column without being aware of it. So what will happen? Delta Lake will block this update because we have the schema enforcement enabled by default. And that's the type of message you can have. But of course, we won't block you because we know that your schema may change. You may end up adding one or multiple columns. As you can see here, like we have a table with column name and age, and then we ended up adding a new column called country. In this case, you just need to add a specific option called merge schema equal to true, and the mode needs to be append. And in this case, like every time you're going to add a new column, it will be added without any problem. And of course, you can track this in the time travel feature. And of course, you have another option called auto merge that you can activate. And this like disable this feature, which means like whenever you add a new column, you don't need to add this specific feature, but please make sure to use it only if you're aware of what you're doing, because this can be quite convenient, but also dangerous. So keep this on your mind. And of course, we can not only add new columns. What if we need to remove a column or maybe change the type of a column? Then for this case, you need to, let's say, overwrite our table. And you need to specify an option where you specify the overwrite schema equal to true. And this gives you flexibility, but always keep in mind that you can always time travel and go back to the previous schema. And we have generated columns. And when this feature was introduced first, I was truly amazed. Why? Because it's a special type that uses a column that can be computed by Delta using a specific function. And for my example, the one I'm doing here, so I have a birth date, which is a timestamp, and then I'm adding two columns called month of birth and year of birth. So technically what I'm doing, I'm casting the birth date and by month, and casting the birth date by year to get those new columns, which means when I'm gonna insert like just the four columns, automatically the last two columns are gonna be computed by Delta. And this is super, super awesome. And you will also find something interesting that you have generated by default and generated always. So generated by default, which means if, for example, the data is not filled, then I would insert those columns. So it's going to be the case where you want to introduce like better data quality. And generated always means even if this column is filled with some specific data, it will always be overwritten by these generated columns. And we have identity columns, which is a derivative from generated columns. This identity columns is also super, super awesome because you can create unique values. So the case over here that I'm using, I'm creating a primary key, and again, a big int. I'm specifying that it's type big int, generated always, and then I can start like which value this column will start with. And here I'm specifying that I will start with 0, and then each time I'm adding a new row, it will increment this by 1. And you can be sure it will never create a duplicate keys, which means you can also rely on this feature to make sure that you don't have data redundancy and make sure you clean your data in a super efficient way. And you can combine them both, of course, identity column and generated columns. So you're gonna ask me a question. What are the advantages of both of them? So first, for generated columns, as I did mention, those are really great way and automatically to consistently populate like your Delta table. But it's also super awesome way like to have fast, efficient storage. Why? Because you can persist those generated columns in a storage, which can be very, very savvy, because they are done only on when they are saved on compute, because they are run only when you want to have these features. And then last but not least, you can also you use those generated columns to partition your tables in case you want to use Hive-style partitioning. So the case over here, like you can generate those partitions, for example, have timestamp, then you can create 2 new columns like month and year, and then partition by those 2 new columns. So you can also benefit from Hive-style partitioning and improve your data skipping. And what about identity columns? So you can make this like as a unique identifier to make sure that you don't have data redundancy. You can also make sure that you have efficiency insertion and prevent error prevention by not adding like some duplicate keys that may end up breaking your pipeline. But also they have compatibility because identity columns are similar to one you can find in relational databases. And flexibility, because as I did mention, I started my identity column by 0 and I did increments by 1. You can change this step by making 2, 3, or 4. So you have flexibility. And what about merge operations? So merge operations, let's suppose you have a table, let's say customers, and then you have a view like with some bunch of new data. So how can I update my table? So what you can do, you can use the merge operation. And here, as you can see in the code, so you just need to specify the condition. So for instance, you can use those primary keys to join those 2 tables. You may say, okay, I need to verify that the customer that I have in this table, the customer ID that I have in this table, exists in the other table. When it's matching, then I can say, okay, maybe I need, so then in this case, I can update the source, or maybe I need to drop this specific customer. And you can set conditions like if it's matching, insert. If it's not matching, delete. You can think about several options. And at the end, you're gonna have statistics like how many data I inserted, how many data I deleted, how many data I updated. And to make sure that you have fast merge operation, first of all, make sure to have deletion vectors enabled, we discussed before, and make sure to narrow down the search space. So what I mean this first search space, because here I'm specifying the when matched, which means the condition is like source key equal to target key. But you can add additional filters like when matched and age is higher than 18 and city equal to San Francisco. This will speed up the merge process. And what about checks and constraints? So those are super, super important also to have great, let's say, data quality. So the first one is the not-null constraints. So you can think about this like a way, let's suppose you're inserting some data, but you don't want to have, I don't know, a last name, empty last name, or empty birth date. So what you can do, you can specify that this column cannot be null. And during the insertion process, if one column does not match this expectation or this condition, the insertion will fail. So you need to make sure that you have a good data quality. Of course, you can do this while creating the table, but also after the table creation, you can just add this constraint. And then we have the checks. And the checks are also very important because sometimes you may end up having data in this specific column. But how can you check that this data is respecting the conditions you may have? For example, I don't know, you may have age, and then you end up adding that your age is 125. So can be the case, but it's rare. So you can add this condition that if it's higher, do not insert this data. And you can be sure that you can have a good data quality. And how you can do this, you can just add as many checks as you want. Like for this case, I'm calling it date within range, and I'm adding this condition where date is higher than the 1st January from 1900. Of course, you can add many checks if you want. And last but not least, one of my favorite features, it's liquid clustering. So liquid clustering has been introduced with Delta 3.0, and it has some awesome capabilities. But before discussing what's liquid clustering, I'm pretty sure you all know, I've been aware of liquid, Hive-style partitioning, where you can have a table and you do some partitioning, which means within those files, you're gonna have some file skipping. You can partition by, for example, by country, and then it will improve, like when you are looking for a specific country, for example, USA will go straight to the country, avoiding doing multiple scans. But what if your data keeps growing? And then you want to partition add a new partition like country and maybe city. In the past, you had to do what we call the overwrite because the schema is changing, we're doing a lot of stuff. So it's an overwrite, and it can end up being a little bit expensive if your table is big. So what we did, we introduced a new functionality called liquid clustering. So the purpose over here is to have a logical clustering instead of having something physical. So how does it work? So you can just create your table, and at the end you add cluster by gender, for example, for instance. For my case, it's cluster by gender, but you can have up to 4 columns. I don't advise you to go higher than this so far. And if you want to disable this liquid clustering, so you can just take cluster by none. And that's it. So, and what's the goal over here? So the goal is really to have this logical partitioning, and it can evolve. For example, instead of partitioning by country, I want to change it. It's just alter table and add a new clustering key. It's very easy. I can keep changing this, like for example, based on my behavior. Like in, let's say this month, I'm like doing a lot of filters on the country. Next month, maybe it's gonna be on a product. So I can keep changing without paying without, let's say, having like a large compute to run. Because it's just logical clustering with some statistics captured. And then the last but not last thing, the bonus of it is that when you run the optimize, which is like optimize the compaction of the files you have in your delta table and also capturing statistics. Now when you run the optimize, it will only run on the incremental data, which means if you run it in the past and then you add two rows, when you run the optimize will be very fast because it will only be on the incremental data. And then you're gonna ask a question, how can I, or which column should I choose to cluster my table? So if in the past you used to partition your table by specific columns, you can take those columns and use them as clustering keys. If you used to use like z-ordering, you can also add the z-ordering column in the clustering key. If you think for some reason that you may have some skewed data, just add this column in the clustering key, because the liquid clustering will also handle this skewed data to make sure that you create new leaves. And also, like if you think that a column the access to this column may change over time, just add it. It's not a big deal. It would be very easy to change it. And last but not least, tables like the column where we have concurrent writes requirement, because we're adding more flexibility and more better handling of concurrent queries. Thank you.